This is Chapter 4, Part B. In this video, we're going to be extending our conversation about the node voltage technique. We're going to be looking at another example of node voltage, working all the way through it. We're going to be doing a couple of special cases for node voltage, so things that show up along the way. There's others we won't get to in this video. And we will talk about supernode, which is something that a particular issue that shows up with node voltage circuits that it helps to have a kind of a custom way of handling the situation. I don't know, it could have been 5 minutes since you saw the last video. It could have been 5 days since you saw the last video. So I want to start just by doing another example of node voltage. It never hurts to do a lot of these. The good thing is this year with the online recording, if you don't want another example and you feel good about it, you can skip it. But in general, usually students really just want lots of examples of these sorts of problems being done. And so we're gonna do one, just nothing special, just another node voltage problem to kind of do a refresher of the process we do for node voltage. So we have a circuit here, and our analysis with node voltage always starts by labeling all of our essential nodes. And again, I always like to label them, like this. Okay. And now we choose a reference. I always like the bottom of the circuit, but usually you want a connection with a lot of branches on it. So we're going to call this our 0-volt reference. Now we're going to label the other two nodes. I'll just name them A and B this time. Sometimes it's V1, V2. Sometimes it's A and B, whatever gets the job done. And so now the node voltage technique says that each one of these nodes, write the Kirchhoff's current law equation. So we're going to write the equation that says the sum of the currents flowing out of this node is 0. Sum of the currents flowing out of this node is 0. And that should give us our two equations. Should give us our two equations, two unknowns. We can solve for these node voltages A and B, and then from there we can find any other unknown in the circuit. Starting at A, the current flowing to the left is going to be VA minus the voltage on the other side of the resistor, which since we had 0 volts here and we went up 144 volts, we are at 144 volts right here. So the voltage on this side was VA, the voltage on this side was 144, so it's VA minus 144, that's the drop across that resistor, and then to find the current, it's the voltage drop across the resistor divided by the resistance, which is 4 ohms. And then the current flowing down from node A is going to be VA divided by VA minus 0. So we just write VA divided by 10. And then the current to the right is going to be VA minus VB divided by 80. And I guess I labeled them A and uppercase A, uppercase B, and now I'm using lowercase subscripts for the voltage. So I shouldn't do that. I apologize, but it felt natural. So, and that total current is equal to 0 by Kirchhoff's current law. Now we'll go around to B, and the current to the left is going to be VB minus VA divided by 80. And then the current down with this 3 amp supply is 3 amps flowing into node B. So if we want to know the current flowing out, which by convention we're writing the sum of the currents flowing out equals 0. So if there's 3 amps flowing in, that means there's negative 3 amps flowing out. And then the current flowing to the right is going to be VB minus 0 divided by 5. And that equals 0. Okay, so this is looking pretty good so far. So, and again, this is the process, this is the node voltage process right here. It's this. It got us to this point where now we have two equations, two unknowns. Now this is just a matter of algebra. But as I've also said before, I always hated when I was in school when they would just say, oh, now it's just algebra, and they wouldn't do it. And again, you have the ability to fast forward. So let's just crank through this algebra a little bit here. So again, I hate fractions. So I like to multiply, I know you spend a lot of time on least common, lowest common. I just multiply each function by something that's going to clean up those fractions. Whatever is kind of the easiest looking thing. So even if it's bigger than the lowest common or least common denominator. So I'm just going to multiply the top one by an 80. So multiplying the top one by an 80, we get, I'm just going to move all the way over here. We get 20 VA. And then that's going to be minus 20 times 144. That should be 2880. And then it's going to be plus 8 VA. And then it's going to be plus VA minus VB. And that equals 0. Okay. And we're going to multiply this bottom one by 80 as well. That didn't help anybody. We're going to multiply this bottom one by 80, if you can see that. So that one's going to be VB minus VA plus 240 plus negative 240 plus should that be 16? Okay, and that's my two equations here. And let's clean them up a little bit now. So we're going to clean up the top one to be, looks like I have 20 plus 8 plus 1. That's 29 VA minus VB. Flopping that negative 2880 to the other side is 2880. Doing the same thing with the second equation, it looks like I have a total of 17 VBs and negative 1 VA. So negative VA plus 17 VB equals 240. Hopefully that made sense to everybody. Okay, so now again, I always like to, if I'm going to get rid of something and I already have a negative VB in one equation and a positive VB in the other, for me, I'm just going to multiply this expression both sides by 17. So if I multiply both sides of that by 17, I get 297 times 29. So I'm getting 493 VA minus 17 VB. Let me check. Yeah. And that should equal 48,960. Okay, I think I did that right. Hopefully I did that right. Nope. Oh wait, yeah, that's right, sorry. Doubting myself here. So then I'm just going to add to that the expression negative VA plus 17 VB equals 240. And when I do that, I get 492 VA equals 49200. Well, that was nice. So if 492 VA is equal to 49,200, that means, just making myself more space up here, VA equals 100. And then plugging that back in, let's take this expression, rewrite it up here as VB equals 240 plus VA divided by 17. That's going to be 240 plus 100 divided by 17. That is So 340 divided by 17 is going to be 20. Cool. So VA, and that's VB. So VA was 100 and VB was 20. Always nice when it comes out clean like that. And again, now that we have that, we can find any other unknown in this circuit. So if we wanted to find the power dissipated by the 5 ohm resistor, then we just do V squared over R. So it would be 20 squared, 20 minus 0 squared divided by R. If we wanted to find the current through this 80 ohm resistor, well, it's 100 minus 20 divided by 80. So it's going to be, looks like it's going to be 1 amp. You know, anything, any unknown in this circuit now, it's fairly straightforward to find once we've solved for these essential node voltages. Okay, hopefully that kind of helped break the rust off a little bit. Now let's talk about what happens when we throw a dependent supply into these circuits. Well, the good thing is it doesn't really change much. The main thing is treat the dependent supply as if it is just a supply. Like treat it just like it's, if in this case, a dependent voltage supply, treat it like a voltage supply as long as you can. And then at the end of the day, you know, this dependent supplies are a function of some parameter in the circuit. In this case, it's this current flowing through here. But the good thing is when we apply node voltage, we have these essential node voltages and we can use them to solve for any unknown in the circuit. So really all we're going to do is once we've written our equations, we're just going to say what essential node parameters do we need to use to solve for this I sigma in this case. And then we just plug that in. So we just you know, whatever combination of essential node variables we plug it in. And the good thing is if we do that, it doesn't add an extra variable to our system. So it's not going to add this variable I sigma as long as I sigma is represented by some combination of these node voltages. Okay, there's another thing though that's happening in this circuit, and that is, look at this branch here. So I believe the book referred to this as an essential branch. It's gonna, we're jumping ahead a little bit, but it's got a resistor and a voltage supply and a resistor. And that's a little hard for us to write our expression. Normally when we do a node voltage analysis, we say, you know, the voltage on one side of the resistor minus the voltage on the other divided by the resistance. But if we're doing this, it's very hard to express the voltage here and here. It's very hard for us to, you know, if it were just, this was our 0 and we just had a voltage supply on it, it would be easy to express the voltage on the other side. But when it's mixed like this, it's a little difficult. And another thing to point out, another trick, is that all of the elements in an essential branch, so all of these circuit elements in this essential branch, we can change the order of these elements without changing the overall behavior of the circuit. That is to say, we can swap around where each one is. We can't swap around the direction of it. So we couldn't flip this voltage supply, but we can switch the order of these components in order to, you know, make it easier to write the equation. And at the end of the day, it doesn't matter. These are all, the nice thing about an essential branches is they're all in series. All the elements are in series, which means they have the same current going through them, which means they're going to all have the same voltage drop across them if they're resistors or voltage supplies. And that means that, you know, there's ultimately you're going to get to the same voltage one way or another. Whether you drop a certain voltage across the 30, then drop across the voltage supply, then drop across the 20, or drop across the 30 and the 20 and then the voltage supply, it doesn't matter. It doesn't change the overall behavior of the circuit. So that's another little trick, that we can switch the order but not orientation of things in series in an essential branch when doing this analysis. So sometimes it really helps to be able to swap around components, combine resistors, you know, move a voltage supply somewhere where it's easy, the math is a lot easier to write. So, okay. All right, let's analyze this. So process, let's clean this up a little bit. Label our essential nodes. I didn't label it the one I like, okay. Do we have any other essential nodes? Remember, an essential node is a connection of 3 or more circuit elements. We do not. These are the only 2 essential nodes. Pick a reference. In this case, both of these nodes have 3 connections, but I always like the node at the bottom. I don't know why. I don't know why the node at the bottom being the reference is so, it's just like a human thing, but everybody likes the reference to be at the bottom. Maybe it's like a sea level thing. We want it to be physically lower on the circuit, not quite sure. Anyway, and then we're going to label our, so we'll just call this one V1. And now at all of our labeled essential nodes, we're going to write the Kirchhoff's current law expression. Sum of those currents equals 0. And as I said before, I am going to make this easier, we can swap the order of these elements. So if we redraw this little branch here, so I'm going to essentially reorganize that branch like this. You might not like that I just said we can do this, that we can just switch the order. But again, this is an issue of if you were analyzing this, if you were writing a Kirchhoff's voltage law around this branch here, you would be doing the sum of the voltage drops. And the nice thing about summation is you can switch the order of things in summation, right? And it doesn't change what the summation is. And that's the principle here. The math, you can prove it to yourself with the math if you want, but that's ultimately what's happening is things in series, the voltages are added, the current is the same, and with addition, I forget what that is. That the commutative property of addition? Commutative? I did know at one point in time the label. I'm pretty sure it's the commutative property of addition, but if not, then I look like an idiot on the internet forever. So with the circuit configured like this, let's now write this equation. And actually, I'll probably do one step further and I'll say 30 plus 20 equals 50. So I will actually write this as a 50 ohm. I'll do even more work. And this is common with node volts. Sometimes we can make our lives a little bit easier simplifying sometimes components in a node voltage analysis. But you want to be careful. You don't want to oversimplify those components if what you were asked to find was something related to a component. So perhaps if we had wanted to find, some specific strange voltage across some collection of values, then we might want to be careful about switching those around, or if we do switch them around, to undo them before we do the subsequent analysis using those known node voltages. So, all right, let's write this equation. So we have, going to the left, we have V1 minus 160 divided by 10. Going down, we have V1 minus 0 divided by 100. Going to the right, we have V1, and again, we're using this version of it, minus, it's going to be 0 plus this, so it's V1 minus 150 I sigma divided by 50 equals 0. And that's it. We have one equation because we only had one essential node. The only thing we have left to do is we have to get rid of this I sigma here. So what is I sigma? I sigma is this current flowing this way. What is the current flowing in that direction through the 100 ohm resistor? Well, it's the voltage on this side minus the voltage on this side divided by 100. Voltage on this side is 0. The voltage on this side is V1, and then we have divided by 100. So I sigma equals 0 minus V1 divided by 100. That's negative V1 over 100. So we're just going to swap that in there. Eventually, I'm going to probably rewrite this equation. Again, looking at this equation, what would you multiply this equation by? I would multiply it by 100 right off the bat, right away. So then we'd have 10 V1 minus 1600 plus, oops, should have called that a V1, plus V1 plus 2 V1 minus 300. And again, we're going to substitute that in here. So 300 times negative V1 divided by 100. So looking at this, right, that's just 3 V1. So I'm just going to all that equals 0. So give myself a little space to work with here, and I'm just going to move up to wherever I got space here. This is a mess. So I'm doing what I always dislike when students do on a test, which is just, you know, move their work all over the place. But I'm trying to work around my own face here. I don't even know why I have my face in the corner. It's just vanity, I guess. I just like looking at myself. I'm not really contributing much except facial expressions. You can see when I'm worried about whether or not I'm doing the math right live. Okay, so our V1s, it looks like we have 10 V1, 11 V1, 12, 13 V1, 16 V1. 16 V1, and then flipping that negative 1600 to the other side is 1600. All right, so we found V1 was 100 volts. Cool. So that's it. That was it. You know, the analysis with a dependent supply was fairly straightforward. We treated it just like it was a voltage supply. We just wrote, you know, the voltage on this side minus the voltage on the other side. And then it was just a matter of plugging in another equation for that. It didn't really add, it didn't add an extra equation in the sense of it didn't add an extra unknown variable that we had to produce another equation to solve. Well, I guess it kind of did, but we just directly substituted that. We just wrote that variable as a function of our labeled node voltages, and then it didn't really add much complexity to the process. It's just a little bit of extra math. And that's what you do. The biggest thing is, though, don't forget these dependent supplies, they're just supplies. It's just a voltage supply. So treat it like a voltage supply in pretty much any other way. All right. So let's go with some more special cases here. So on this one, we talked about what happens when there's a really inconvenient collection of things in series. And we said you can kind of swap the order of them. Let's look at some other things. So let's start analyzing this circuit here. I created this circuit, and I did not create this circuit to come out clean. So it definitely doesn't come out clean, and I'm not planning on solving it all the way. I'm just going through this math to sort of give you the exercise of how to put this stuff together. So we are not going to solve this, and if we did, the math would be beastly, which is okay. It's okay to do these and have the math be not clean. It doesn't have to be clean, and if you take a test or a quiz, you wouldn't necessarily expect it to be clean. But sometimes for the sake of these videos, I prefer the clean ones because it just, you know, makes it not take so long. So label all of our essential nodes here. And again, this labeling nodes like this, it's not the way other people do it, but it's the way it helps me. It really helps me just to show the little stub sticking out, just so I know, here's all the elements that are actually connected to this node. Choose a reference. That one looks good to me. Label V1, V2. Now let's start writing this equation. So starting at V1, sum of the currents flowing out equals 0. So at V1. What's this current down here? It's going to be V1 divided by minus 0 divided by 75. What's this current down here? Uh-oh. Uh-oh. Now we have an issue. What is the current to this voltage supply? No idea. We have no way of writing this current to the voltage supply. Ultimately, how would we have to, if we had to find this current to this voltage supply, after everything was said and done, how would we have to do it? We would have to do it using Kirchhoff's current law, because there's no resistor in this essential branch here. There's no way for us to represent an equation for current. The current flowing through that voltage supply is just going to be whatever current's left flowing in or out of that node to make the current flowing in equals the current flowing out. And so we have an issue here. But whenever you encounter this, if you're doing a node voltage and you encounter a situation where you say, that's weird, I can't write there's no way I can write an equation for the current here. Stop. You know, as soon as you feel that, stop and say, okay, there's something going on here that I need to think about how to deal with this. And here's what's going on in this case. What's going on in this case is the voltage at this node is known. So we created a variable V1, and we started trying to write an equation that includes V1. But in fact, we don't need to do that because this is not an unknown node voltage. What is the voltage at this essential node? the voltage of this essential node is 25. How do we know that? Because we had a labeled 0 volts here and we went up 25 volts, so we're at 25 here. So this node's voltage is 25, and that happens anytime. So the special case here is this case where we had a voltage supply between our reference node and one of our essential nodes. And that means that now if there'd been a resistor in there, we just have to solve it. If there had been a resistor in there, of course, it's like any other, just V1, you know, the voltage of the node minus the other voltage divided by the resistance of that resistor. But if there's no resistor there, then we just know that voltage of that node. There is another case where when you have a voltage supply between two labeled nodes, then you can't just say it's 0 volts plus something, and so that's the voltage. And that's where we'll talk about it. It's another special case. We'll talk about it next. But when you have a voltage supply between an essential node and your reference, then you don't have to write the equation for that essential node. You know the voltage of that essential node. It's done. It's 25 volts in this case. And so let's keep going though. Let's keep going here. So now we have, so we don't have to worry about that because this is a special case where we have this voltage supply here. At V2 though, let's write the current flowing out here. Okay, so at V2, we have, through that top 10, we're gonna have V2 minus 25 divided by 10. Through this current supply, it's gonna be -3. Down through here, it's gonna be V2 minus 0 divided by 40. And then what about in this direction? This might seem a little strange. We have a current supply, but we also have a resistor here. One of the biggest mistakes students make when they're doing node voltage is if they see something like this, they just instinctively say, oh, there's a supply. And they'd write the equation, they'd write V2 minus 2 divided by 50. And that is wrong. Because this is not a voltage supply, this is a current supply. But the resistor throws them off. What does this resistor matter? So in general, resistors that are in series with a current supply have no real impact on a circuit. If you put a resistor in series with a current supply, of course, the resistor is dissipating power. It's got some current flowing through it, but it doesn't impact the rest of the circuit. Why? Because the circuit doesn't care if you connect a current supply or a current supply in series with a resistor. It's still going to be the same supplied current. It's going to be the same current flowing through. It's going to be the same current flowing out of this node or into this node. In this case, what is the current flowing out of this node? It's going to be -2. So this resistor actually didn't matter. It is still a real resistor. We could still solve for power, but it doesn't have any impact on the rest of the circuit. Also, the same thing is true here. A resistor in parallel with a voltage supply has no impact on the rest of the circuit because, you know, there's still this fixed 25 volts. No matter how many resistors you put in parallel with a voltage supply, there's still going to be 25 volts between the terminals. And so as far as the rest of the circuit's concerned, it doesn't matter. It's still volts, still the same maintained voltage. If you got a couple extra resistors just burning current, that's fine. And they're there and they matter if you're calculating power or something else. But if you're just looking at how that impacts the rest of the circuit, a resistor in parallel with a voltage supply doesn't impact the rest of the circuit. Okay, so that's just a couple little things that can show up that I want to just mention so people know. And this is my resulting equation here, and maybe it's clean. I'm kind of curious now. All right, if you don't want to explore this curiosity with me, then skip ahead, but I'm just going to see what happens if I multiply this by 40. We got 4V2 minus 100 plus -120 plus V2 plus, multiplying this by 40, -80. We got 5V2 equals, whoa, look at that. It's gonna happen. It came out clean. I totally just made these values up and it came out clean. Unless I did something wrong and it came out clean because I did something wrong. What are the odds of that? Sometimes just got to go with it. Whatever. We just got to go with it. It worked out in our favor. Like when you throw a regular Pokeball at like one of those dark red circle Pokemons and like somehow it catches it just with a regular old Pokeball. I don't know. You get lucky. You gotta take the wins when you get them. Okay, now this is the real special case for node voltage. This is the one that is an issue, and you do have to do something special unless you recognize it and follow the sort of special case for us here. So let's just start analyzing this. Okay, everybody agree? These are our essential nodes. Now let's do, that's my pretty obvious 0 there. We'll call this one VA, we'll call this one VB. Okay, and at VA, let's just write this equation for the currents flowing out. It's going to be 2 plus VA minus 0 divided by 50 plus, this is where we start to run into trouble, is we have a voltage supply between two labeled essential nodes. And so we can't just say the voltage on the other side of this is 0 plus 25 or 0 minus 25 or something like that. We don't know, the voltage on the other side is VB, but we don't know the current. We have no way of writing the expression for current. We do have to do something for this. This is not, these essential nodes are not something we can just get rid of in this case because it's not a supply between our 0 volt reference and our essential node. One thing we could do is we could, if we encounter this, we could just go back and label like VA, label that 0 or label VB 0, and then actually that is a trick to fix the problem to a limited extent. You can't always fix the problem, but for right now, we can't do that. So how are we going to have to write this current flowing here? Well, we're just going to have to just create a variable. We're going to have to call it I, whatever. There's some unknown current. We don't know the current through that 25 volt supply, and there's no way for us to say, oh, looks like I don't need to solve this, so we just gotta create a variable, and this hurts because the whole point of the no voltage technique is to minimize the number of variables. So if we're just creating variables, it really stings. It's the opposite of what we're trying to do, but that equals 0. Okay, so now at node VB, so this one was at VA, now at VB. Now immediately we have this kind of same issue with the current to the left. Well, the good thing is we'd already labeled this current I flowing in this direction. So the current flowing in the other direction now is just going to be negative I. And then the current flowing down is going to be VB minus 0 divided by 150. And then the current flowing to the right is going to be, we could combine these into a 75 just to make our life easy. And that's going to be VB minus 0 divided by 75. And all that equals 0. Okay. Well, the good news is we have these two equations. And if we add these two equations together, we can get rid of this 1. So let's add these two equations together. So we got 2 plus VA over 50 plus I plus negative I plus VB over 150 plus VB over 75, and all that equals 0. And those I's go away, which is great. And let's just multiply this equation by 150. So we get 300 plus 3VA plus VB plus 2VB equals 0. Okay, great. Awesome. Here's the problem though. Because we combine these equations to get rid of that I, we're short an equation. So where do we get that other equation from? Well, we get that equation from this supply. We got to go back to the supply. It's not meaningless. It still impacts our circuit. It's got to be somewhere in these equations. And in fact, what does this voltage supply tell us? It tells us there's 25 volts between VA and VB, or it tells us that VA is 25 volts higher potential than VB here. Clean this up a little bit. I probably shouldn't have done that. Yeah, so it's saying basically that VA minus VB is going to be 25. So that's our other equation. VA minus VB equals 25. And now this is something that we can substitute into our expression. If you're playing the game that I play, you would just multiply this by a 3 and this by a 3, and you would say, and then it would be moving over here, you'd have 300 plus 3 VA plus 3 VB equals 0, and then you'd have 3 VA minus 3 VB equals 75. Again, we're multiplying that whole thing through by 3, and then you'd add them, and then you'd get 300 plus 6 VA equals 75. So minus 300. And I'm running out of space here. VA equals negative 225 divided by 6. This doesn't feel very good. I'm getting negative 37.5. Maybe it's right. Maybe I made a math error somewhere. If I made a math error somewhere, minus a couple points for me. I don't know. So hopefully, anyway, I mean, I wasn't, my point was mainly to show you how to analyze that. The good thing is we're actually going to get a chance to take a second shot at this. So this approach that we did here is fine. What we did here, we had to create a variable to solve for this unknown, and we had to cancel that variable out, and then we had to add this other, we had to use the voltage supply defining the potential difference between the two nodes to create this extra equation to solve for this. Now, let's treat this as a special case. This and the technique the book teaches, I'm not even sure the technique the book teaches is really necessary. As long as you recognize what we just did here and you're able to do that, that's fine. The book kind of has a way to write this equation directly, though. The book gives you a way to, or sorry, the book gives you a way to write this equation directly. So we'll talk about that. So this technique is called supernode. Supernode is anytime you have a voltage supply between two labeled essential nodes. The book basically says, treat this as, and this is, let's just be consistent and call this VA and this VB. The book says basically that you can treat this whole, you can take the voltage supply out and pretend that there's a wire here for now, and basically treat this like one giant node. And you can write the Kirchhoff's current law flowing out of this giant node, this supernode, if you will. So if you write the Kirchhoff's current law flowing out of this supernode, that will give you the equation that you need. Let's give it a shot. Now here's the thing, when you do a supernode, you still have to remember this is still VA and this is still VB. So your equations for these currents will still reference VA and VB. It's just going to be that, you know, it's just going to be that, that you're writing it all in one step here. So the current's flowing out, this plus this plus this plus this. That's going to be 2 plus VA divided by 50 plus VB divided by 150 plus VB divided by 75 equals 0. And if we go back, that's, oops, that is the same thing we had here. It's an absolute disaster on this page right now, but that's the same thing. VA over 2, VA over 50, VB over 150, VB over 75. Yeah, 2 VA over 50, VB over 150, VB over 75. So the supernode is when we recognize a voltage supply between two labeled essential nodes, we can treat that labeled essential node as a single node from which we write the Kirchhoff's current law. And that makes sense because Kirchhoff's current law does still apply. Anytime you're talking about any region of a circuit. So you could say, you know, the net current flowing into or out of this whole region of the circuit has to be 0. It doesn't have to be one node. It can be any chunk of the circuit. If you have any chunk of the circuit, if that chunk of the circuit for some reason has a net current flowing into it or a net current flowing out of it,
right to jail, right away.
Right? That's really bad. If you have a net current flowing into your region of the circuit and there's nothing flowing out, well, it's the whole electrostatic issue, accumulation of charge, and then things blow up. So let's finish this. I kind of want to go through the math one more time to make sure I didn't flub the math on that last page. So let's go through it one more time. So we have this equation here, and then we still have to add that second equation. So we still have to add this VA minus VB equals 25. Okay, let's do my math maybe a more traditional way here. So the more traditional way would be to say that, you know, get this into some form. VA equals 25 plus VB. And then substitute that in. So let's take this equation and I'm still going to clean it up. Multiply it by 150, doing the math one more time. We get 300 plus 3VA plus VB plus 2VB equals 0. That's 300 plus 3VA plus 3VB equals 0. And then plugging this in for VA here, we have 300 plus 3 times 25 plus VB plus 3VB equals 0. That gives us 300 plus, I guess this time I'm solving for VB accidentally. So, I mean, it doesn't matter. We just add or subtract 25, but that's what I'm doing. 300 plus 75 plus 3VB plus 3VB equals 0. And then hopefully you can do this. I'm just going to jump ahead to one step because I'm running out of room. And I'm just going to say VB equals negative 375 divided by 6. And hopefully everybody saw why that is the way it is. All right, so negative 375 divided by 6, we get negative 62.5. And that was VB. And then VA is just going to be that plus 25. So and that equals, negative 37.5. So either I was right before, or I'm very consistent in my being wrong. Either way, I'm feeling pretty good. Either way, I think bodes well for me. Consistency is important, even if it's being wrong. All right, so that is the supernode. And the supernode approach is this specially named technique that the book uses to refer to how you deal with a situation where you have a voltage supply between two essential nodes. And the main thing is, if you're doing node voltage, note that voltage supplies are tricky with node voltage. With node voltage, when you encounter a voltage supply, you have to be very careful about, is this voltage supply touching a reference node so I can just, you know, take 0 plus or minus whatever that voltage is? And if it's not, then you got to be very careful about, okay, can I use the supernode technique for it? And if there's a resistor in series with the voltage supply, then you don't even worry about it. Then it's just that you just write the equation as you would normally. But voltage supplies are with node voltage, what you have to be very careful with. Current supplies are easy. Current supplies are easy because you're writing Kirchhoff's current law equations. So if you have a current supply, you're just given, a current supply is just telling you what the number is for that current flowing into or out of the node. So current supplies are easy, voltage supplies are the ones that are tricky for node voltage. So that is all that we're going to talk about for node voltage for now. And when we continue next time, we're going to talk about the complement to node voltage, the node voltage technique, which is called the mesh current technique. So it's basically everything you can guess, everything we do with node voltage, which is choose a bunch of nodes and write the Kirchhoff's current law equation at each of those nodes. We're going to do the complement for mesh current. So we're going to choose a bunch of meshes, which are those little loops in the circuit. And we're going to write the Kirchhoff's voltage law equation for each one. And that's just giving you a taste of it. And you can guess pretty much everything in this class kind of has a complement, voltage to current, current to voltage, and that's it. So until next time, thank you for watching.